So let us give a short introduction to segment routing v6. The heart of the segment routing v6 solution is the network programming model. You know that in segment routing, we express the program that we execute on the network as a list of instructions. And this list of instructions are represented as 128 segments. They have the form of an address. And this list of instructions, of segments, are placed, the first instruction is placed in the destination address. And if the network program requires more than one instruction, the remaining instructions are placed in the segment routing extension header that we saw in the previous recording as reach the proposed standard status, SRv6 status, and so it's completely mature from an IETF standardization viewpoint. And so here we have an example with a network program of 3 instructions. We have the first instruction in the destination address and 2 instructions in the segment routing extension header. As we will see, it's very likely that the network program can be expressed with one single instructions, in which case the first instruction and alone instructions will only be in the destination address, and actually you will not need a segment routing extension header. The type of instructions that we have defined in order to have an open interoperable solution at the IETF are, for example, instructions related to traffic engineering and fast reroute. They are the so-called end and end.text. Very easily, this is the shortest path to a node and a shortest path to a node followed by a forwarding adjacency over a specific chosen link. And then we have obviously VPN instructions that are doing decapsulation and cross connection on a chosen attachment circuit, or decapsulation and lookup in a VPN table. In this presentation, we see, in this slide, we see on the top the IPv6 header where the destination address will hold the first instruction. And so then we focus on this segment routing extension header, and there we have a tag that's going to be very useful for group-based policy. Then we have a segment left, which is really like a pointer in the network program to tell us where we are in the list of instructions. What is the next instructions to bring in the destination address? Because the one in the destination address is always the so-called active instruction. It's the one that is being executed. And so then we have a list of instructions, and we see that in this slide we report an instruction as having 2 parts, a locator part and a function part. And that's obvious, is that the first part, the more specific bits of the instructions are called locator. They really act as a routed prefix. The owner of that instructions, the one that can execute that instructions, is going to advertise a locator prefix in ISS or BGP, and you can think of it as a /64. There's no constraint, you could do what you want, but it's easy to think about it as a /64. So the owner of instruction 1 here would advertise, hey, I am locator 1/64. And so when that instruction would be in the destination address, very easily the packet will be routed along the network according to the shortest path to that node. When the packet will get to that node, the node will say, hey, the locator 1 match, it's me. So I am able to understand the remaining bits. And these bits are called the function bits. They basically encode, they are mapped to a behavior that needs to be executed by the node. And this could be a traffic engineering function, it could be a fast reroute function, it could be a VPN functions. This is the power of these instructions that can be mapped to everything. But they could also be mapped to an NFV application, to a VM, to a container, etc. So that's the first part of the segment routing extension header, which has really been optimized for hardware processing. And this is really optimized for functions that would be executed at line rate by the hardware at large scale. So functions that are of the type of fast reroute, TE, and VPN. Then in the bottom of the segment routing extension header, we have the metadata TLV. And there you could find user information, credential, performance data. Basically, the structure of that part of the segment routing extension header has been optimized for NFV integration. We want the different services that are integrated as part of 5G SRv6 solution to be able to pass information to each other. For example, the deep packet inspection can record some information on the packet in the metadata TLV, and other applications can basically leverage this information. So that's really the philosophy of that segment routing extension header. We see that it has reached the mature status of proposed standard. It's RFC level at the IETF. It has 18 hardware line rate implementation with multiple public interrupt reports and 8 public deployments. These deployments have been reviewed in the previous recording of this multi-part recording that I'm doing in February 2020. So in SRv6, it's important to understand the notion of SRv6 domain. That's basically the service provider domain where the service will be built in order to transport customer packets. So the SRv6 domain is in blue. The customer packet will get through the green interface and get out of the domain on the other side of the domain. And what we want to really highlight is that when the customer packet comes, and it can be an IPv4 packet, an IPv6 packet, a layer 2 packet, we don't care. It's always the same. We always encapsulate it. The ingress P number 1 of the SR domain will encapsulate the received packet in an other header, which is IPv6. So the SRv6 solution can be used to transport any kind of service, IPv4, L2, and as well IPv6. The other header pushed by the ingress P is IPv6. And there, depending on the network program, if we need more than one instructions, then we also have an SRh in this other IPv6 header. But if the network program, and we will see this is very frequently the case, only require one instruction, all what the ingress P will do is IP in IP encapsulation, so it will be the addition of an IPv6 header. The packet is follows its path through the SRv6 domain. The network program is executed. We reach the egress PE, where basically the added IPv6 header and potentially the SRh are removed. The inner packet in green is given to the customer side on the right. And obviously, the customer packet received on the ingress P is exactly the same as the customer packet given on the other side of the domain. There are zero modification. It's obviously, that's the basis of any service, is that you can never tamper with the customer packet. And this is obvious, and we want to underline it. We obviously provide end-to-end integrity to the customer packet because all of the SRv6 network programming operation is applied to the outer header that is pushed at the ingress P and removed at the egress P. So the customer packet is completely untouched. It has end-to-end integrity. If you look at it, it's exactly like what would have happened in an MPLS domain. You can find this recording at this link, and in the coming weeks and months, we will likely provide additional videos in order to delve into some details of the SRv6 solution. So many thanks for your attention.